Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about the polarization of electromagnetic waves, classical electromagnetic waves. Now, the first thing you may wonder is why are we talking about classical electromagnetic waves in a course about quantum mechanics? Well, as you probably know, a quantum mechanical treatment of electromagnetism leads to the concept of a quantum mechanical particle known as a photon. And we're going to be talking about photons a lot in Physics 323. And one of the characteristics of a photon is that it has a polarization associated with it. And if you want to understand what we mean when we talk about the polarization of a photon or the polarization state of a photon, it really helps to remind yourself of what polarization is all about when you describe electromagnetism, electromagnetic waves classically. So let's remind ourselves about how polarization works with classical electromagnetic waves. And I should say that the discussion in this episode of What's the Big Idea really follows the discussion that's given in the extended polarization tutorial that is posted on the course website. So I suggest that you both listen to this What's the Big Idea, which sort of gives, as the name implies, an overview. But then you really want to sit down with the PDF document, the polarization tutorial, and go through that rather carefully. So Maxwell's equations tell us that an electromagnetic wave consisting of an electric field, an oscillation in an electric field, and an oscillation in a magnetic field can propagate at the speed of light through a vacuum. And the electromagnetic waves are transverse waves. If they're propagating in this direction, which we'll call the z direction, then both the electric field and the magnetic field lie perpendicular to the direction of propagation. And in this drawing here, the electric field is directed along a direction which we're calling the x direction. The magnetic field is directed along a direction which we're calling the y direction, and the electromagnetic wave is going to propagate in the z direction. And when an electromagnetic wave like this interacts with matter, it's usually the interaction between the electric field and say, the electrons in the matter that are the most important source of interaction. So it's useful to concentrate on the electric field, and we're going to talk about the polarization of the of the wave as being related to the direction in which the electric field points. So we would describe the wave shown in this picture as a wave which is polarized in the x direction, linearly polarized in the x direction. And we can give a mathematical description of the electromagnetic wave using the two equations that are shown right here. So what we see from the mathematics here is that the electric field is directed along the x direction, because I hat is a unit vector along the x direction, and the electric field has an amplitude E naught, and it is a cosinusoidal oscillation propagating in the z direction. And we would describe this form as a plane wave because the electric field only depends on the z coordinate. There's no x or y dependence on the electric field. So as you move in the xy plane, the electric field remains constant. It only varies as you move along z. And similarly, the magnetic component here is a cosinusoidal oscillation of amplitude B naught. That's this distance here is amplitude B naught. And if the waves have a wavelength lambda, then this parameter here, k, which we call the wave number, is related to the wavelength lambda by k equals 2 pi over lambda. And this parameter here we recognize as the angular frequency of the wave, and that's related to the actual frequency nu by a factor of 2 pi. And then the ratio of the angular frequency omega to k, it's easy to see, is just the same as the product of lambda and nu, and we know that that is the speed at which the wave propagates at, which of course is the speed of light, c. Now again, the wave that's shown here is polarized along the x direction. There's no y component to the electric field, and that's clearly a special case. We can consider a more general case in which the electric field has both x and y components. So let's do that now. Okay, so let's consider the more general case. We started off on the last slide with a wave that we're just focusing on the electric field, and previously the electric field just had a component along what we were calling the x direction, along one direction. But now we're going to consider a case in which the electric field has components potentially along both the x and the y directions. It's still propagating in the z direction here. And not only that, but the phase between the x and the y components may not necessarily be zero. So the more general case again is represented by these two equations here: the x component and the y component. X component directed along I hat, y component directed along j hat. And now these different components in general have different amplitudes, which we're going to call E naught sub x and E naught sub y. And the phase difference between the x and the y components is going to be denoted by this phase angle phi. So in this first example here, there's no y component, there's just an x component. And we say that that wave is linearly polarized. In the second case here, we have circular polarization of light. And in circular polarization of light, the amplitudes of the x and the y components are the same. These waves here have equal amplitudes, but they differ in phase by 90 degrees, or pi over 2 radians. And then more generally, you have waves in which the ratio of the amplitude of the x component to the y component can be anything, and the phase difference can be anything. And we call such waves, this general state we refer to as elliptically polarized light. And there's a nice app from Wolfram Alpha that's linked to from the polarization tutorial that lets you play around with different polarization states. So there's a slider and you can control the ratio of the amplitude of the x and the y components and the phase difference between them. And you can sort of see what the wave is going to look like. And you press play here, and the thing will evolve over time, so you can sort of see a lot of information by playing around with it. The wave that's shown here has an amplitude ratio of 1. That means the x and the y components are equal, and a phase difference of 0 radians. So what you get is still a linearly polarized wave, but the direction of polarization is, in this case, at 45 degrees relative to the XY axes. Okay, so the next thing I want to talk about is the various optical elements that we can use to alter the polarization of a light beam. So a common optical element that can do that is a polarizer. A linear polarizer. They're simple ones that you can get. They're found in sunglasses that are just sheets of plastic that have what's called a transmission axis. You send polarized light into a linear polarizer, and only the components of the light that lie parallel, of the polarization that lie parallel to the transmission of the axis of the polarizer make it through. So that leads us to a scenario here where you send unpolarized light in, and the intensity is cut in half. And then now you have linearly polarized light directed in one particular direction, and that light enters a second polarizer whose transmission axis makes a angle theta with the orientation of the polarization that's incident. And the law of Malus says that the intensity after that second polarizer is going to be cut by a factor of cosine squared theta. Another class of ways in which we can alter the polarization of a light beam is to rely on materials that are birefringent, optical elements that are birefringent. And by birefringent, we mean that the index of refraction of the material is different depending upon the orientation of the polarization with respect to some axis within the material. So this figure shows the action of a birefringent material that we'll call a retarder. And these birefringent materials have what's called a fast axis and a slow axis. So the index of refraction is smaller, and therefore the light beams travel faster for the components of the polarization that are parallel to the fast axis of the material. So what ends up happening is that depending on the thickness of the plate, you can end up with a phase shift of the beam. So you have light that's linearly polarized coming in. So the two components of the polarization are in phase, and then due to the birefringence of the material, you introduce a phase difference. And if you pick the thickness of the material appropriately, you can end up introducing, say, a quarter wavelength phase difference, a 90-degree phase difference between the two orientations, as is shown here. So you start off with linearly polarized light, you end up with circularly polarized light over here if you have what's called a quarter wave plate. And this figure here shows how you can use a birefringent material to separate out the two different polarizations of the light. So you come in this situation with light that has components polarized both in the blue direction in the plane of the figure and in the red direction perpendicular to the plane of the figure. And then this birefringent material has its fast axis or optic axis oriented at some angle here. And then it turns out that what happens is that when you have birefringent material, the two different polarizations go off in different directions. The red direction sort of obeys Snell's law, which means it goes straight through, but the blue component ends up bending the way is shown here. So you end up with the polarization that's in the plane of the figure coming out in one location on the plate, and the polarization perpendicular to the plane of the figure coming out in the other orientation perpendicular to the plane of the figure. And this ends up being, as we'll see, a very useful device in the kinds of experiments that we're going to talk about in a bit. If you take a look at Beck chapter 3, you'll see that this device is pretty central to a lot of the arguments that he gives when he talks about the behavior of experiments involving single photons. Okay, so here's our expression for how the electric field of our plane polarized wave varies as a function of position z and time t. And the polarization state of this wave, remember, depends on the amplitudes, the relative amplitudes of the x and the y components of the wave, and also the relative phase between the x and the y components. And everything at this point is a real quantity. An electric field is a real physical thing, and every number here is just a real number. And it turns out that there's a trick that you can play in which you introduce complex numbers into the story in a way that ends up making life a lot simpler due to the mathematics of complex numbers. So let's see how that works. Okay, so the first thing is the basis of this trick is really going to be Euler's formula, Euler's relationship. The fact that the complex exponential of the form e to the I theta can be written as a real part that's equal to cosine theta plus an imaginary part equal to sine theta, okay? And so Euler's formula means that we can alternatively represent this real quantity of the electric field by taking the real part of these two quantities that involve complex exponentials. The real part of e to the I kz minus omega t is just cosine kz minus omega t according to Euler's formula. Now, why is that a useful thing to do? Well, to see why, let me remind you of a very basic property of any exponential function, not just complex exponential functions. If you have any exponential function, say something of the form e to the a plus b, that you can write as just e to the a times e to the b. Okay, aha. So why is that useful? Well, this property here really enables you to factor out the phase information here. Here you have this e to the I times the sum of kz and minus omega t and phi, and we can just factor out the phi, e to the I phi, just by making use of this property of exponential functions. So why is that useful? Well, if you look here, all of the information about the polarization of the light wave is contained in this factor here. And that form really leads to this idea that we can define this quantity called the Jones vector, which contains all of the polarization information about the state of the light beam. And I'm not going to go into the details right now about Jones vectors, but I want you to read carefully in the polarization tutorial about exactly how this works. And then the other really useful thing about this formulation is that we can represent the action of optical elements like polarizers and birefringent plates we can define the action with a matrix quantity called the Jones matrix, and you can then calculate the effect that interaction with that particular optical element has on the polarization state just as a multiplication of a matrix times a vector. So you have something whose polarization state is initially Jn, it interacts with some optical element characterized by a matrix, the Jones matrix M, and you get the new polarization state just by multiplying that matrix times a vector. So very useful way of dealing with polarization, Jones vectors and Jones matrices. And so then the last thing I'll say, and this is really the rationale for why we've spent so much time talking about classical polarization, is that this approach dealing with polarization, specifically this idea of Jones vectors and Jones matrices, which you'll read about in the polarization tutorial, that approach is strikingly similar to what is going to be the quantum treatment of the problem of the polarization of individual photons. So it's the time that we invest here in understanding how to describe polarization of a light wave classically is time well invested, because we're going to use a lot of this machinery or something very similar to it when we deal with polarization quantum mechanically. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye-bye.